Hi and welcome to another edition of Ordinary Differential Equations. Today we are going to talk about method of undetermined coefficients for a general right hand side. Let's go ahead and take a look at this case, which happens to have quite a bit of algebra involved in it. Okay, so we are talking about the method of undetermined coefficients. We are going to paying attention to how to choose our pet functions for the particular solution. And we are going to deal with the so-called non-resonant case. I'm going to talk about this thing later on, but all the examples that we are going to take a look at today are from the non-resonant case. So what was the problem? The problem was that we had a differential equation, second order, and the right hand side was some pet function. You remember pet function refers to combination of polynomial, exponential, and trig. Last time we went and dealt with the most important case of this. That is, the right hand side is a trig function, sine or cosine of some frequency. Now, mathematically, the method can be applied to any of the pet functions. That is, if the right hand side was some exponential times some mix of polynomials and trig functions, we can apply same idea as before, meaning for our trial solution or the particular solution, we are going to take exact same type of function, except that the coefficients in these two locations are going to be undetermined, and then we are going to determine them later on. The notation might be a little bit intimidating here, but the idea is very simple. So let me explain what's involved here. So this is some exponential that you have. This P and Q are some polynomials of degree n and m. And then you have some trig functions, sine and cosine of some frequency times time. The frequencies are the same frequency. The idea is that the trial function that you use, remember the particular function that has to be added to the homogeneous solution to give you the general solution, it is created out of the family of these. The family simply means you are going to replace the P and Q here by some general polynomials as yet of undetermined coefficient, and then you are going to go ahead and find them later on. Let me go ahead and take you back to the previous lecture for a second so that this discussion here wouldn't look too theoretical to you, and then we come back to this page again. So you remember last time we had, for example, a differential equation, second order, right hand side was some cosine of 4t, for example. And then the solution comes into two steps. One is that we strip the right hand side and find the homogeneous solution that we call response of the system by itself. And then the particular solution, which is a solution of this equation to that stimulus from the right hand side. The way we go ahead and find the solution, we get the family of this function. The family of either sine or cosine is made out of both of them. So we take a combination of sine and cosine with some as yet undetermined coefficient. These C and D are undetermined coefficients. We take the guess and plug it back into the equation, make the two sides agree, and from that we find the C and D. Well, the idea is very general, and it is applicable to all pet functions. Just to make it clear, I made a list here. On this column for f of t, I'm writing some examples of what might appear on the right hand side. Y of p is what you are going to start with undetermined coefficient, and then you try to determine these coefficients by plugging it back into the equation. So let's just quickly go over this list. This list is trying to explain the general idea that we had there. So if right hand side is just a trig function, either sine or cosine or a mixture of them, then your particular solution is family of these, which is some multiple of a cosine and some multiple of a sine. If the right hand side is just an exponential, for example 8 exponential of 3t, then your yp is family of this thing, which is some multiple of same function. If right hand side is just a pure polynomial, here we are some examples of second order polynomials. This one is just t squared, this t squared and a number, this is t squared and a t and a number. In all three cases, your trial function, your y particular, is going to be a complete second order polynomial, at squared plus bt plus c. And then if you have a product of these things, we essentially have product of these things. So let's just go ahead and take a look. Suppose I have an exponential times a trig. Then the family of this thing is my exponential times the combination of the sine and cosine of the same frequency. If I have an exponential times a polynomial, then my trial function is exponential times a full polynomial. Regardless of what second order you got here, you always write a full polynomial here. What other combinations could we have? For example, you could have a polynomial times a trig. This type of things don't occur in practice all that much, but mathematical coverage tries to be complete. So we are putting all the things that we can do under the same umbrella. So if you have a polynomial times a trig, you consider both sine and cosine, regardless of what you got here, so both the sine and cosine, and for the coefficient, you put the full polynomial that you see. Now here's another example. I have both sine and cosine. One polynomial is t squared, another polynomial is 2t. I go with the highest power of this thing. So this is order 2, this is order 1. I pick second order polynomial, and so on and so forth. This is another example. Again, same kind of particular is going to be applied. The finale is having all three functions. If you have exponential and polynomial and a trig, then your job is going to be a bit more extensive. Your trial function is going to be exponential times all of this. All of this parentheses has both sine and cosine, and the coefficient of the sine and cosine is highest degree polynomial that you see here, allocated with both of them, each of them having their own coefficients. A problem like this is going to be quite extensive because you have to find 6 coefficients. Some of the homework problem just asks you for that. It doesn't push you to actually go ahead and find ABC, because that becomes a 6 by 6 linear system to be solved. Quite a bit of algebra. Typically, problem like that gets to be solved by some computer or something. So in those type of questions, you just indicate what the trial function is going to be, but you don't need to carry out the whole calculation. So the idea was that if we have these pet functions, polynomials, exponential, and trig, then we start with the same type, except that the coefficients are not known for us. And we always complete and pad our trial function with having both sine and cosine and considering a full degree polynomial. That's how we get it started. Now, all of this applies to the so-called non-resonant case. I explained last time that actually that is the more significant issue. We have both pure resonance, we have partial resonance, and that's a very interesting engineering question. You want to essentially, resonance means you are getting the most out of a certain situation, or you're protecting against the most destructive force in a certain situation. So that is going to deserve its own separate lecture. We are going to talk about it in several instances. So I'm going to postpone that to the next lecture. Just to briefly mention what the issue is. We said in applications, A refers to mass, B refers to the drag coefficient, C refers to the spring constant, and F is the driving force of the system. This is the energy that comes from the outside. Now, if the energy that comes in resonates with the system itself, then the system is going to absorb the energy and it's going to have a very big response that we refer to it as resonance. Mathematically, and that refers to the situation that one of the expressions that you have on the f of t matches the solution of the homogeneous equation. Homogeneous equation by itself is the equation where the right hand side is 0, that's where no driving force, and essentially you're considering the system oscillating by itself. If your external force matches the internal vibration, then you have resonance and you have a very interesting situation. Mathematical description of it, again, we are going to postpone to a separate lecture so that we keep everything separate. Okay, so this was a short lecture. Exercises from this section is going to be a little bit extensive in terms of algebra. If the problem becomes extensive, then we are going to have some software that's going to help us cut through that and get us our coefficient rather easily. Okay, until next lecture, good luck and God bless.